So now we'll look at finding the value of the actual definite integral. So it's easier to use right endpoints when you find the definite integral. So what we're going to be doing is looking at the limit as n goes to infinity of this expression. So notice what this is. So my right endpoints are going to be k over n, where k is my counter from 1 to n. And so those are my x values that I'm going to evaluate this function at. So I replace x with k over n in that function. So I'm taking the sum of that function evaluated at k over n multiplied by delta x, because that is the definition of the definite integral, the limit of this Riemann sum as n goes to infinity. So we're going to use, this is where we're going to use those summation properties, those formulas, to simplify this thing, to find this limit. So notice a couple of things. The sum involves k and n, but only k is changing. N is the final value. So we can treat this 1 over n and these instances of n, we're going to factor those out. And we're going to just be looking at these expressions in terms of k. Let's look at some basics of summation. So a constant added to itself n times is given by this expression, and that's just multiplication. If we have the sum of a constant times our terms, we can factor that constant out. So we're going to be able to factor this 1 over n out. That's just a constant. And then the associative property, so that it says that the sum of two functions added together, I can take them separately as the sum, the addition of the sum of each function. So now we need to look at these formulas, because this is where we're going to be using these when we find the definite integral. So notice that in that expression that we had, we have k squared in one sum and k in another. So what we're going to do is first we're going to use that associative property, which says that we can break each of these terms up into their own sums. And then we're going to factor out that 1 over n from inside that summation sign, because we're only summing with respect to k. So now I have the sum from k equals 1 to n of k squared, and I use this formula. So I can replace this summation with this value. Looking here, I can factor out that 4 from that sum, and now I have the summation from 1 to n of just k. Going back here at the summation of the first n integers is this expression. So I can replace that summation with n times n plus 1 over 2. And then finally I have the sum of just this constant 2, and that's just multiplying, that's adding 2 to itself n times, which is just multiplication. So that's just 2n. So now I have 3 different limits. I'm adding them together, and those sums are gone and the k's are gone. So now I take the limit of each of these terms, and I'm going to simplify a little bit. Cancel the n's. So I have a rational expression here. The leading coefficients are 2 in the numerator, 6 in the denominator. So this limit goes to 1/3. This is just a rational function. This limit goes to 2, and the limit of a constant is 2. So I have 1/3 minus 2 plus 2, which is 1/3. And remember, when we estimated this with the Riemann sum, our estimate was 0.33, which is an estimate of 1/3. Now let's look at one more thing. We can also find a definite integral by finding the area if the the area made underneath a curve is a common shape. We know how to find the area with just geometry formulas. So for example, we can evaluate this definite integral by looking at the graph. So I'm looking at the definite integral from -1 to 2 of 1 minus x dx. So here's the graph of 1 minus x. And notice that I have the shape of a right triangle here and a right triangle here. So knowing that the definite integral gives us net area, instead of trying to figure this out with Riemann sums, limits of Riemann sums, I can just take the area of this right triangle, the area of this right triangle, and I notice I'm going to be finding the net area. I'm going to be subtracting this area from this area. Remember, these are going to give me, the Riemann sums are going to give me negative values here because the function's negative. And the Riemann sums are going to give me positive values here. So these are going to take away from the sums here. So the area, the net area, is 2 minus 1/2. The area here is 2. The area here is 1/2. So this definite integral is 3/2. That's the net area.